A device generating linear or rotational motion using carbon nanotube as the primary component is termed a nanotube nanomotor. Nature already has some of the most efficient and powerful kinds of nanomotors. Some of these natural biological nanomotors have been re-engineered to serve desired purposes. However, such biological nanomotors are designed to work in specific environmental conditions. Laboratory-made nanotube nanomotors, on the other hand, are significantly more robust and can operate in diverse environments including varied frequency, temperature, mediums and chemical environments. The vast differences in the dominant forces and criteria between macroscale and micro/nanoscale offer new avenues to construct tailor-made nanomotors. The various beneficial properties of carbon nanotubes makes them the most attractive material to base such nanomotors on. Just 15 years after making the world's first micrometer-sized motor, Dr. Alex Zettel led his group at University of California at Berkeley to construct the first nanotube nanomotor in 2003. A few concepts and models have been spun off ever since, including the nanoactuator-driven bithermal gradient as well as the conceptual electron windmill, both of which were revealed in 2008. Here A is area, C is capacitance, F is electrostatic force, E is electrostatic field, L is length, V is voltage, and Q is charge. Despite the scaling nature of the electrostatic force, it is one of the major mechanisms of sensing and actuation in the field of microelectromechanical systems, and is the backbone for the working mechanism of the first NEMS nanomotor. The quadratic scaling is alleviated by increasing the number of units generating the electrostatic forces seen in comb drives in many MEMS devices. Just as the electrostatic force, the frictional force scales quadratically with size f tilde L2. Friction is an ever-plaguing problem regardless of the scale of a device. It becomes all the more prominent when a device is scaled down. In the nanoscale it can wreak havoc, if not accounted for, because the parts of a nano-electromechanical systems device are sometimes only a few atoms thick. Furthermore, such NEMS devices typically have a very large surface area to volume ratio. Surfaces in the nanoscale resemble a mountain range, where each peak corresponds to an atom or a molecule. Friction at the nanoscale is proportional to the number of atoms that interact between two surfaces. Hence, friction between perfectly smooth surfaces in the macroscale is actually similar to large rough objects rubbing against each other. In the case of nanotube nanomotors, however, the intershell friction in the multi-wall nanotubes is remarkably small. Molecular dynamics studies show that, with the exception of small peaks, the frictional force remains almost negligible for all sliding velocities until those special sliding velocity is reached. Simulations relating the sliding velocity, induced rotation, intershell frictional force to the applied force provide explanations for the low interwall friction. Contrary to macroscale expectations, the speed at which an inner tube travels within an outer tube does not follow a linear relationship with the applied force. Instead, the speed remains constant despite increasing applied force, occasionally jumping in value to the next plateau. No real rotation is noticed in non-chiral inner tubes. In the case of chiral tubes, a true rotation is noticed, and the angular velocity also jumps to plateaus along with the jumps in the linear velocity. These plateaus and jumps can be explained as a natural outcome of friction or peaks for growing velocity, the stable side of the peak leading to a plateau, the dropping side leading to a jump. These peaks occur due to parametric excitation of vibrational modes in the walls of the tubes due to the sliding of the inner tube. With the exception of small peaks that correspond to the speed plateaus, the frictional force remains almost negligible for all sliding velocities until those special sliding velocity. These velocity plateaus correspond to the peaks in the frictional force. The sudden rise in sliding velocity is due to a resonance condition between a frequency that is dependent on the intertube corrugation period and particular phonon frequencies of the outer tube, which happen to possess a group velocity approximately equal to the sliding velocity